Hi, this is Shivam and I'm going to be presenting Module 3, which is our module on the general linear model. So let's begin by getting into what is the general linear model. So the general linear model aims to uh, find the relationship between a particular outcome, which is a dependent variable, and the various predictors. And along with that, there are certain constants within the model, and it also accounts for a certain amount of error. Um, the model itself is general additive, and it is based on a model, which means that the variables can be tweaked as per uh, the interest of the researchers or anyone who is deciding to use it. It is additive, so you can stack the effect of various predictors on the particular dependent variable, and it is model based, which means that it can be used to propose theoretical strategies for various phenomena. And as you can see, that this makes the tool pretty versatile. What helps is also that there are certain assumptions that keep the various data points within the model kind of neat, such that analysis can take place fluidly and smoothly. So let's get into MRC versus ANOVA. So MRC and ANOVA are two forms of uh, the general linear model. There are two ways in which you can use it for multiple for multiple regression and correlations. What you can do is it's basically used to assess the influence of predictors on outcomes. And for ANOVA, it compares the different variances between the means of different groups. Now, with MRC, if there is a particular error, it's associated with the model or the way that the data has been processed by the model. Vis-a-vis in ANOVA, the error they say that the error is part of the the instances or each particular instance of the variable. Let's get into the similarities between the MRC and ANOVA. And as you can see, because it comes from the GLM, it has a certain amount of similarities. So the first one is that it deals with variances. Additionally, it has similar styles of hypothesis testing in different forms and ways, and it also has similar assumptions underlying the model. So I'd want to talk about the assumptions first, and then as you and right after that we'll go ahead and analyze it uh, in the upcoming slides. So the first assumption is that relationships between predictor and outcome is linear. It can be represented in the form of a line. The predictor is sensible for the outcome, which means that they do one predictor can precede or logically precedes the the outcome. Um, the fact that it says no more predictors, it means that the the model itself is self-contained. There are no additional variables required which would predict the particular outcome variable. There is no measurement error or bias, which means that all the error that we see is random and it's not part of any measurement that we've taken. Of course, we know that this is not completely 100% true as per Cortina, but it's something that we do assume at the same time. The mean of the residuals is equal to 0. The variance is constant for all values of the predictor, which means that the data is homoscedastic. Additionally, the error is not correlated and it is random. And again, the predictors are uncorrelated with the error terms, and you'd find that the errors are normally distributed. Some of the assumptions of now, while ANOVA has very similar assumptions of MRC, there are certain independent assumptions that it makes. The first one is that each case is independent. There are no overlapping cases within the data. So data from one case has not been repeated twice. The errors are identically distributed across all groups within which that are going to be studied, and the distribution of errors is normal. So let's get into the MRC analysis. What I want to share with you is the MRC that I've run on three predictors x1, x2, and x3 with the dependent variable y1. So just from a cursory glance, we can see that. So let's talk about the data first. So as per Cortina, we did not use any dichotomous variables because that's not what MRC would deal well with. So for all the predictors that we've used, they are either interval or ratio here and here. So that's one thing which we're going to look at. And additionally, what we see is that what we're also going to consider is that the standard error that we're keeping into account is of the unstandardized coefficients, and that's because Gary King said that although this is going to be lower than a standardized error, what it's also going to be able to provide us is a truer picture of what's going on. So as per the results here, there are no significant, so no predictor has a significant effect on the dependent variable y1. As we can see here, we see that this is kind of close, but we'll see why later on. I've decided not to remove any outliers from the equation. Additionally, if I'm going to be looking at the variance inflation factor, none of it is such that it would concern me, which shows that the data is not multicollinear. That's something that we can see from the variance inflation factor. So let's go to the data. We're just going to take a cursory glance to see if we see any particular outliers, and we can see that as of now there is none. Maybe one here, but again, we'll talk about why I have decided not to remove any pieces of outlying data. Okay, so as I mentioned earlier, since there are some positively correlated predictors here with one another, such as x1 and x3, we're going to go ahead and look at this, and as we can see, the variance inflation factor is low, so that's something which is out of the way there. All right. So another thing is, are the residuals independent? So as we can see here, the Durbin-Watson statistic is fine. It's around at 2. So by that, there is no autocorrelation within the various residuals. Now we're going to look at if there were any outliers. So the interesting thing here is that I was a little bit lenient with the centered leverage value. And I took a mean, I multiplied the mean by 0.3 to see if I multiplied the mean of 0.1 by 3 to see if there was any outlying data here. So here, this was one of the maximal, this was probably close to 0.3 here, but I decided to include it because of what I read in Cortina, where we need to represent our data completely, and it was also within the bounds of what was agreed upon before I ran the analysis, which was 3 times the mean of the centered leverage value. Is if a number falls within that, I'm going to include it. Additionally, here you can see that the Cook's D as well is something which was concerning, but since it was just within the bounds of that plus 1 number, I have decided to include that. Hence, I have not removed any outliers within the data. Another thing that we're going to look at is to see if the residuals are normally distributed, and as we can see here, the means of the residuals is 0, so that's another assumption that we have met. Here we can see that although by the PP plot that although the residuals are not completely aligned with the line of best fit, as the data tends towards as we get more and more observations, we've got only 30. As we get more and more observations, this line should kind of come closer to that line of best fit. And here, from a cursory glance of the regression histogram, we can see that there is no value which is outside the bounds of our normal distribution, so that's good too. Here we can see that since looking at the spread of data here, that nothing really looks homoscedastic. Nothing looks heteroscedastic, so it seems that most of the data here is unidirectional, and so we're good there. If we were to look at the dependent variable here, we can see that with reference to skewness, although the data is slightly negatively skewed, it should be fine. The dependent variable is slightly negatively skewed, it's fine. Again, although the data is slightly flat, it is within the bounds of normal or acceptable. So we're just going to hold on to this. So that's something which is cleared. Okay, moving on to ANOVA. So just looking at the data here, there we can see that there is no significant factor. I looked at the F tables online as well, and F was less than F max in each case, and hence we failed to reject the null hypothesis. Hence, no factor has any effect on our overall model or on our final dependent variable. Additionally, 21% of the variance in the dependent variable could be attributed to changes in our factors. So here we're just going to, as per the check for homogeneity, we see that Levene's test has been rejected. We failed to reject the null, and hence the data is fine, it is homogeneous. With reference to the spread of the dependent variable, what we see is there is no significant outlier outside of the normal curve, hence there are no significant outliers that we have found. With reference to the assumption of independent cases, that would be best known through a treatment of the procedures of how the data was collected. Regardless in every case, the data that we used was interval and ratio scale, hence we are going to assume that each case was independent in nature. So that's all for my rendition of module 3. I have included the hand calculations in the comments of the video. Thank you so much.